specifically in the Earth and the Moon really ceased to be an object of inquiry for astronomers.
In the early 70s, Shoemaker's attention turned to the apparently empty sky.
Our next step was to see what were the objects that made these craters. The only way to answer that is to go to the telescope and scan a large part of the sky and see what's coming by. This is the first time ever that anyone had attempted to go and systematically survey the space near the Earth for Earth-crossing bodies, asteroids and comets that could hit the Earth. At the time we started, only slightly more than a dozen of these things had ever been discovered in the entire course of astronomical observation.
This was not surprising, since the rocks he found were tiny by astronomical standards. Faintly reflecting the light of our sun, they could just be picked up on photographs, drifting against the starry background. But the more Shoemaker looked, the more he saw.
This is in the constellation of Scorpio.
Dr. Fry, notice the position of these new bodies.
Yes.
Now, just how fast they've been moving and their eventual destination are among the mathematical problems now being determined by our differential analyzer.
Despite their faint image, these were not pebbles. These streaks represented huge mountains of rock weighing millions and millions of tons, all with the potential to hit Earth. While for decades astronomers had been probing the galaxies beyond our solar system, we had ignored what was right under our noses. Belts of rocky debris had long been known to orbit the Sun, but none of it was meant to come near Earth. What was going on out there?
Essentially, there are two catastrophic machines in the solar system which are directing missiles at us. One of them is the asteroid belt, which is regularly perturbed by Jupiter in its orbit close to the asteroid belt. And the other one is the so-called Oort cloud, which is perturbed by the galactic environment. Both these sets of perturbations result in asteroids or comets being deflected from their normal places into the center of the solar system, where they may be trapped through further interactions with the circulating planets. And it is the ones that are trapped that are potentially dangerous. We're a kind of target amongst all these bodies milling around which have come from places further out in the solar system.
Over a certain size, the atmosphere no longer shields the Earth's surface from these rocks. For instance, something 100 meters across could easily impact still traveling at 20 kilometers a second. And at that velocity, it would do a lot more than make holes in people's cars. One man who appreciated the destructive potential of these rocks was the Nobel Prize winner Lou Alvarez. In 1980, he and his son Walter were investigating a peculiar event in prehistory. 65 million years ago, over half the world's species disappeared, including the dinosaurs. Alvarez had a vision of what might have caused it, and it certainly wasn't uniform or gradual. Nice idea, but it all smacked of catastrophism, and the reaction of paleontologists was predictable.
I think it was almost universally negative. One can find a few who were not negative, and of course this number increases with hindsight, but no, I think to a first approximation we all found it an appalling idea.
There were many other more terrestrial explanations for global havoc, such as climatological change or massive volcanic eruptions, none of which required such a gigantic act of God.
Paleontologists are accustomed to think in terms of long-term geologic processes affecting the evolution of life. And if you now suddenly tell them, well, occasionally a stone the size of a mountain falls out of the sky and produces a global catastrophe, they just don't like that. It's against their scientific religion, if you will.
We didn't know anything about what had been learned through the 60s and 70s about meteorite impact and the impact rates, because we had grown up with our textbooks which said that there indeed were bombarding asteroids and comets, but this was all in the early days, the so-called early bombardment of the Earth, and it was all over. And sure, Meteor Crater was probably an impact crater, but that's only one. It couldn't affect geologic history.
But something killed the dinosaurs, and the Alvarez theory compelled scientists to consider seriously an extraterrestrial force.
It stimulated much new data, but more importantly, it has put paleontologists in communication with the rest of the scientific community. And so we're interacting with astronomers, with geophysicists, with geochemists. And this is wonderfully stimulating for both sides.
Theories began to fly. If rocks could cause one mass extinction, why not others? Perhaps the Earth was periodically visited by devastating swarms of meteorites. Indeed, the geological records seemed to show there was a regular pattern of extinctions.
So we suggested that extinctions occurred in a clock-like way. That is, not all extinctions, but pulses of extinctions every 26 million years. This we published, and the astronomers, they're a rather gullible group, picked up on this and suggested a wonderful array of possible astronomical, solar system, or galactic explanations.
There were invisible planets, twin stars, galactic clouds, and giant comets, all just theories. But the cataclysmic demise of the dinosaurs captured the public imagination, and after a century of ridicule, catastrophism had something to shout about. Meanwhile, other astronomers had followed Shoemaker and started hunting for the rocks in near space. They joined in the tedious task of searching photographs of the night sky. The discovery rate increased enormously when the system was computerized with CCD cameras, acting like unblinking electronic eyes, and far more sensitive to any movement of these objects. Soon the astronomers were reassessing the size of their task.
In fact, we've only discovered maybe 5% of the total so far, and if we continue at our present rate, it will take us another 500 or 600 years before we discover 99% of them. However, the total number of astronomers involved in looking for Earth-threatening asteroids is in fact less than the staff of something like a high street McDonald's restaurant. Okay, that is the number of people worldwide that we're talking about looking for asteroids.
We know, for example, there are about 2,000 larger than a kilometer, a few 100,000 larger than 100 meters, and 150 million or so larger than 10 meters. But none of this was known just a few decades ago. We're in an age of discovery.
Steve Ostro took the search a step further when he managed to pinpoint one of these mysterious rocks with radio telescopes.
We've never seen an optical picture of any Earth-crossing asteroid. And this is a little bit ironic because we do have pictures of all other classes of major solar system body. The gaseous planets, the solid planets, their moons, ring systems, and main belt asteroids now. But we have no pictures of any Earth-crossing asteroids because we've never sent a spacecraft to any Earth-crossing asteroid.
While some astronomers concentrated on getting pictures of the edge of the universe, this was the first image of our closest companions in space, the faint radar trace of Castelia, a huge dumbbell-shaped rock rolling over and over. 2 years later, he had more warning and captured the near-Earth asteroid Doomsday. At last, these dark monoliths were giving up their secrets.
It's obviously undergone an extraordinary history of collisions for the past, at least 10 million years, several tens of millions of years. It's unlike any other object that we've ever seen. It's in an unusual rotation state, so it's not just spinning around, but it's almost as if it's tumbling.
Doomsday is 4.5 kilometers long and 2 kilometers wide. In 2004, this huge asteroid will come within 4 lunar distances of Earth, the closest approach of any asteroid that we are likely to see, at least that we know of.
Imagine for a moment if, instead of these objects being not visible to the naked eye, they were suddenly made visible. Suppose that there was a button you could push and you could light up all the Earth-crossing asteroids larger than about 10 meters. There would be over 100 million of these objects in the sky, and you'd go outside at night, and instead of being able to see a few thousand bright stars, the sky would be filled with millions of these objects, all of which are capable of colliding with the Earth, and all of which are moving on slightly different courses through the sky at slightly different rates.
An image which would have truly terrified ancient societies. But if we do drift through such a swarm of rocks, why doesn't the Earth bear the scars?
Erosion takes its toll. Rain and wind and weathering of the rocks lead to the filling in of craters. Nature abhors craters. She fills them in on the surface rather quickly, so craters disappear. So what we had to look for was the deformation in the rocks, the wound in the earth, as it were, beneath the crater. And now we know how to recognize that. The crater doesn't hold its original shape. The walls collapse downward, the floor comes up, and what we've learned to recognize as an impact structure is a ring structural depression where the rocks have been depressed in a donut-shaped ring, and then there's an uplift in the center.
Geologists have started to recognize craters all over the Earth. Almost 200 have now been identified. Computer modeling and small-scale experiments have confirmed why these wounds run so deep. It's all a question of megatons.
If we get to a really big event, say a 10-kilometer crater, which is still small compared to the biggest, that's equal to the energy of all of the nuclear weapons in the world. If you heap them up in a pile and set them off, 10,000 megatons makes a 10-kilometer crater.
This was the sort of event that Alvarez suggested could have finished off the dinosaurs. But no one had pinpointed the scar. Just recently, geologists found some telltale signs beneath the Gulf of Mexico. Although now completely invisible on the surface, measuring the density of the rock underneath reveals a 65-million-year-old wound. A huge, ringed depression, almost 200 kilometers across.
Finding the big buried crater in Yucatan was a major step because we found the smoking gun. Really, we found the smoking cannon that produced the catastrophe at the end of the Cretaceous.
Scientists have modeled the effects of an impact the size of Yucatan on today's Earth. This is a simulation of seismic waves shrieking round the globe at ballistic speeds. While much of this was guesswork, paleontologists found these hypotheses very attractive.
The rocks falling out of the sky could produce one extinction pulse, then I think we must expect, if not assume, that other extinction pulses also have been caused by this mechanism. And as Shoemaker has delightfully pointed out, when we realize that rocks do fall out of the sky on a regular basis, this becomes acceptable in a gradualistic framework, because it's part of the Earth's environment, which we accept and understand.